Okay, let's get back to where we were. Okay, okay, that's okay, Pratima. If it was not showing, we have you in the chat, so it's all right. Um, so we were talking about the Stern-Gerlach experiment. So that you could use as a preparation technique, right? So if you put basically the magnetic field along the z direction, so let us say this direction is the z direction as shown here, then you get this up and down with respect to that particular direction along which we have the magnetic field, right? So so if you if we pick only the spin up particles from the z direction, right, and send them through z direction, you will get all the 100% deflection upward. But if you then send these through another Stern-Gerlach experiment, which is along the x-axis, you would see that again in that ensemble again you have a split along the x-axis, right? So these are not collapses of a single system, but rather reproducible frequencies. So just to contrast with the Copenhagen interpretation, wave function is not a state of a single system, like in Copenhagen interpretation it says, right? Wave function is something, a mathematical tool to generate the ensemble statistics. Measurement causes collapse in Copenhagen interpretation, and this collapse is said to be instantaneous. But the wave function first is not physical, and second thing, there is no such thing as instantaneous collapse. Let me make sure that we are recording it. It is recording. Okay. And then superposition, again, because it talks about state of a single particle, right? It is saying that the particle is simultaneous, the cat is simultaneously alive and dead. But actually what it means is that in the ensemble interpretation, that if you did this multiple times, you find sometimes the cat is alive, sometimes the cat is dead, right? So there is no collapse and no superposition. During the break, I was having a candid conversation with Dr. Gargi, and we were talking about these different interpretations and how there is probably no way to prove it, right? And then I wanted to mention something like, for example, going back to the Einstein's quote, you have two explanations. One is this somehow coming up with these supernatural, non-common sense things, and another that sounds more commonsensical. So if you put yourself, go back to the caveman, right, who thought that gods are angry and that's why it's flooding, right? Versus, okay, it's actually because of the weather, which you can predict, which was way beyond the capability of the caveman, right? So then you would think that, okay, this is right, that gods are angry, so it is flooding, right? So to me, Copenhagen interpretation is something like that, similar to saying that gods are angry and hence it is flooding. It works, right? And in the sense that uh, the math is the same. That is, when it floods, you need to run and hide somewhere, no matter whether it is gods are angry or whether it is due to weather, right? So in a similar way, whether it is Copenhagen or ensemble, the results are the results. The experimental results are the experimental results. But going by the Occam's razor, and then you want to go for the simplest explanation, then for me, in my point of view, ensemble interpretation is something that is very commonsensical and makes more sense than the Copenhagen interpretation. Unfortunately, there are a lot of people, we live in a democracy, right? But when it comes to science, democracy doesn't work, right? Because just because 99 people think something is correct doesn't make it right. There could be that one person who makes it right. And so, in that sense, a lot of people follow Copenhagen. So, some of you shared some videos which I didn't watch, which I will watch. But these are all, most of these videos are all based on Copenhagen interpretations that say things like electron is interfering with itself, or that the cat is both alive and dead, and hype up quantum mechanics in some fashion. Quantum mechanics has a lot of useful features. So if you take all this hype out, it's not that you lose the nice features of quantum mechanics. it still has like relative phase and a lot of things like entanglement, that those correlations, they're still observable experimentally. It is just that you don't need this gods are angry with us, therefore it is raining kind of explanations, like in Copenhagen, in my opinion. So that's the contrast that I wanted to draw here. So filtering as a state preparation, that is, we can have sort of a Stern-Gerlach apparatus, and then like I have drawn here. So I can make a Stern-Gerlach apparatus with some silver atoms, and then they're getting collimated through this, and I can put a magnetic field along the z direction, right? So let's say this is the z direction, right? And then suppose I have a screen here, right? I put the screen at some distance, some d, let us say, right? Then I perform this experiment by sending one by one silver atoms, and I collect multiple atoms, just like how we did the Hitachi experiment, right? And then I see that there is this pattern that forms, like with these bands that appear here. Then I keep everything the same, but what I would do is I keep this part exactly the same, but here I would replace the screen with two slits. I would replace the screen with two slits, or even let us say one slit. That slit matches whatever is the top portion. Then I can say that, so this is the Stern-Gerlach apparatus, let us say, right? So, and I have whatever comes through this slit, because this is the z direction, I am always getting spin up. So then I could say that this is filtering, this entire thing is a filtering as state preparation technique. So I can make a Stern-Gerlach apparatus, and I can make my initial state to be spin up. Do you see that? I can use this as a state preparation technique. So we talked about quantum states being in coherent superpositions. So we talked about three things. We talked about discreteness, right, which you can see in something simple like photoelectric effect, right? And then we saw diffraction that you could do with electrons. I showed you a diffraction pattern, and then we saw the Hitachi interference pattern as well. Then we talked about coherence, right? And then I mentioned that we're going to get back to what coherence is, and that's what I want to talk about now. That is coherence. So let us say that I use this Stern-Gerlach to prepare a state along x direction. That is, I make my magnetic field along the x direction. So I have this Stern-Gerlach apparatus where the magnetic field gradient is applied along the x direction. So whichever direction you apply the magnetic field gradient in, you get the splitting along those two directions. So if I apply the magnetic field gradient along the z direction, I get splitting, spin up, spin down along the z direction. If I apply it along the x direction, then I get the splitting along the x direction. So then I can make a hole like how I said in the screen, right? But I can make the hole only after I have measured multiple of these particles, and I have identified where they are hitting, and then I can cut that part of the screen out. So then the spin up x is going through, right? So then I have, let us say, spin up x coming out of this, or I can also write the same state as this, spin x. Now I take these particles and then I send them through another Stern-Gerlach apparatus. Then they are going to split again. Like if I send these spin up particles through, let us say, a Stern-Gerlach apparatus where the magnetic field is along the z direction, then I'm going to get two beams again, one positive z and one negative z, right? So this is a superposition. That is, I could say that the spin up x, that as you see on the screen, is a superposition of plus z and minus z, right? What we want to do is we want to distinguish coherence from superpositions or statistical mixtures. That is, for example, let's say I take a neutron beam that is polarized in positive x direction, right? So I take it in positive direction, and then I split it into plus z and minus z, right? And then I combine them back. When I combine them back, if I am able to get my original positive x state, then we would say that we have a coherence is preserved. That is, I take the positive spin up, right? I take plus x, and then send it through, let's say, a Stern-Gerlach that is along z. Then I would get plus z and minus z, right? And then now, if I combine these and send them through a Stern-Gerlach along x direction, and I get a single beam out along x, then we say what we have is a coherent superposition, right? So you may have a superposition, but you may not have coherence, right? So the coherence means when you recombine them, you get the state. You are able to recover that original positive x state, right? Okay, so so even in the Stern-Gerlach filtering, this is also an irreversible process because you are discarding information, right? As the particle passes through the magnetic gradient, right? You have you can select a particular spin state like I described, either up or down, right? And you can do that selective elimination. So if you send the particle backwards, right, it is not going to again be spin up. You see, like for example, if I have a Stern-Gerlach apparatus that is positioned along z direction, I send a silver particle, it comes out from the up pole, right? Positive z. Right now, this is not reversible in the sense that I cannot gain information about what was there before. I can only have information about what has happened after the Stern-Gerlach apparatus, because this entire part is my state preparation procedure, right? So that's why I'm calling it an irreversible process, right? So Koch et al. Used similar filtering techniques to prepare hydrogen and measure the discreteness and the coherence there. So one of the things that we wanted to we need to discuss is, we said that when we make a measurement, we need to make measurement on, when we make a measurement on one particle, like in this case, when we are measuring in Stern-Gerlach experiment, what we are measuring is the position. Most of the measurements when you measure are actually position measurements. Even energy, it is some sort of a position measurement in the sense that it hits somewhere on the screen, and based on that, you can see what the energy was, back calculate, right? So ultimately, you have some screen or some detector which the particle is hitting, and from there you are measuring, right? That part, putting the screen here and seeing the dots, this is the measurement part, which is different from the preparation part. So now what we want to ask is, let's say I have a particle. Can I clone its state? Can I somehow make an exact clone, exact replica of that state, right? Like for example, I can photocopy a document, right? And that would result in more or less exact information, right? So similarly, can I somehow use some device? Can I build some device where I can clone a given quantum state? Then I can make many measurements. I can make many copies as I want, right? So so then we want to show that that is not possible. This is called the no cloning theorem. And we want to show exactly why that is the case. So what we are proposing is that let's consider some particle in some arbitrary state phi. We do not know what this arbitrary state is. And I'm making a device. The device is itself in a quantum mechanical state, like the Stern-Gerlach apparatus, right? So the electrons in the magnet, they have certain spin, they are in some state, right? And so that device state I'm calling as, the device state is psi. And this device is going to produce an extra particle, right? So you have one particle to begin with. So you have our original particle, right? Our original particle that is going to have a state psi. And our device is in an initial state of psi with, say, n particles. And so whatever I pass my particle through this device, right, which is a unitary transformation, let us say, right? So if you have a unitary transformation where my particle is going through with the device, it is interacting with the device, right? Then the device which has n particles would become some psi prime with n minus 1 particles. And then I get two states that I'm making a copy of whatever is sent in. Are you able to follow me? I'm making a copy of whatever is sent in. So the device state is changing to n-1 particles. There is a question here. Okay, so Shafna, could you please unmute and tell me which part you were not able to understand?
Sir, I was answering for the question regarding the no cloning theorem.
Oh, okay, okay. So sorry, I thought you were saying you were replying to my question about whether you were able to understand. Okay. So here in the no cloning theorem, basically what we are starting with again is we are starting with the device in a state psi which has n particles. Again, this is hypothetical, right? And I have, this is the one that I want to copy. This is one particle which I want to copy, right? One that I would like a copy of. So unitary transformation is essentially, when I say unitary transformation, think of it as like e to the power minus iht by h bar for simplicity, right? That is, there is some perturbation, some interaction with the device. For example, if it is a Stern-Gerlach device, it has to do with the mu dot B. If it is electromagnetic pulse, it would have to do with electromagnetic fields. Whatever is the perturbation, some unitary time evolution, right? So the one particle interacts with the device. After some time, what I'm going to get is the device with n-1 particles and the original particle along with a copy of the particle. Then that is what cloning means, that I have a unitary with phi, that is my particle, and psi, and then I'm going to get phi, and psi prime. So I'm writing it as psi prime because psi prime has n-1 particle. So that one particle is taken out from the device and put it into the state phi, right? So if this works, then we can make exact replicas, right? So then we'll show that why it can't work. So let us say we take two distinct states. Let's say we take a state phi1, one particle in state phi1 and phi2. Again, when I mean this state, what I mean is a preparation procedure, right? Please bear that in mind, right? So let's say I have, for this phi1, I do this phi1 times psi, right? And then I get phi1, and the particle and the device goes to some state psi1 prime, right? And I'm labeling it as psi1 because it is copying particle 1. So when it copies the first state, then basically it is going to change into one particular state. Similarly, I can do on phi2, right? When I do with phi2, then the device is going to be in a different state. It will copy phi2 because phi1 and phi2 are different states. Then the device also has to be different, right? So the device is going to give me psi2 prime. Now, if I consider a superposition state like phi s, which is 1 over square root 2 phi1 plus phi2, and I want to make a clone of this. That is, I want to do u phi s with psi, right? Then what I should get is I should get phi s, again phi s with psi, let's say psi double prime, right? Or let us say psi s prime. That is a device state after copying the superposition state. Are you able to follow me? Any questions? Are you with me? Okay. It will be nice if yeah, okay. Okay. Thank you guys. Okay, at least some of you are following. That's great. So what we show is that now we should get this. This is what we want to get when we clone a superposition state. But quantum mechanics is linear. That is, so let's hold on to this relationship that I'm going to put in a box. We'll keep this aside. And then we will do this math in a different way, right? By expanding out what the superposition is, right? So when I do u of phi s, with the device in psi, right? This u is a linear operator, which means that I can write this as u of 1 over square root 2 phi 1, right, plus 1 over square root 2 phi 2, with the device being in psi, right? So then I could expand this out, then I would get 1 over square root 2 u acting on phi 1 with device in psi, right, plus 1 over square root 2 u acting on phi 2 with the device in state psi, right? And so we have seen what this is, right? We have seen that this is nothing but phi 1 is copied and the device goes into a n minus 1 particle state with psi 1 prime, right? So then I can write this as 1 over square root 2 phi 1 cross phi 1 cross psi 1 prime. And then this similarly would be 1 over square root 2 phi 2 cross phi 2 cross psi 2 prime, right? Clearly, whatever I get here, when I use the linearity, when I expand this psi s out as psi 1 and psi 2 and operate on psi 1 first and psi 2 next, right? Then whatever state I get, right, is not the same as what I would get if I cloned the phi s directly, right? If I clone the phi s directly, like the boxed relationship that I have here, I should get phi s that is cloned from phi s, and then the device returns to this psi state, right? So you can see that what I have up here by linearity of u, where I'm doing this linearly on phi 1 first and phi 2 next, versus copying the phi s itself, these two results should be the same if cloning is possible. But because these two results are not same, that means that you cannot really clone anything. Were you able to follow the proof? Why no cloning is possible? Please answer yes or no. Okay. Okay, let me see, ask the question in a different way. Do you think cloning would be possible if phi 1 and phi 2 are, like, for example, in case of phi s, we see that these two expressions are different. That is, when I operate it as a linearity, right? The expression that I'm getting after linearity of u versus the last expression on the slide. Would these two expressions be the same if phi 1 and phi 2 are orthogonal? If phi 1 and phi 2 are orthogonal, would that matter? Do you see my question? If phi 1 and phi 2 are orthogonal, then would these two expressions match? Okay, I see the answer is no. Okay, let's see, right? So if they are actually discrete orthogonal states, then you can actually copy them. Half instead of 1 over square root 2 factor. So they would match, right? Yes, this should be 1 over, okay. I think I made, that's what you are probably referring to here, Saptagiri, that I missed the.
No, Ram, I was saying if those two are orthogonal, those phi 1, phi 2 terms cancel out 0, 0, and we
Right.
will be left with the other two terms which will match with the phi s, but the common term is 1 over 2 here, but in the linearity term it would be 1 over square root 2. That's why they won't be equal. That's what I understood.
So
It
yeah,
has to be equal to that, right?
So let's do that. Let's do that here. I have that here, right?
Yeah,
So
sure.
yeah. So basically what we are saying is that if I take the first expression, let's say I take u with phi 1 and I have the device in state psi, right? Then I would get phi 1, right? Crossed with phi 1, right? And the device is going to be in state, let's say psi 1 prime. right? And then let's say I have, I take this one, phi2, right? Crossed with psi, right? And I sort of put this on this one, right? Oh, you dagger, something like that, right? So if I put that on that one, the opposite, so first one is the ket that I'm taking, the other one I'm taking the bra. And when I put that, basically what we would get here for this is I would get phi2, right? Cross phi2 cross some psi2 prime, right? So if I multiply these two, then what I'm going to get on one side is phi2, right? With phi1 and psi with psi, right? U dagger U, because it is unitary, would be identity, right? So that's what I would get. And then on the right hand side, I would get phi2 times phi1, phi2 times phi1. So I'm going to get phi2 times phi1 square, right? And then I would get, here I would get psi2 prime times psi1 prime. Here the notation is a bit different on the slide. So we have psi prime and psi double prime, right? So this equation would be satisfied if phi1 times phi2 is 0. Are you able to see that? Right? If I have psi1 times psi2 is equal to 0, right? Then this expression would be satisfied, right? Are you able to see that? So we would say that the classical states which are effectively orthogonal, you can clearly copy classical state, right? So the no cloning theorem from quantum states is not in conflict with copying of the classical states. That's what we want to say, that this is consistent only if phi1. This is in was there a question? Okay. So that's what we mean to say that the cloning is possible only when you have a discrete set of orthogonal states. Any questions?
Can you scroll up to the previous slide?
Yeah.
A bit more. That earlier derivation. Yeah, this one. Okay, then I think then it has to be 1 over square root 2 only, I guess.
So
the last
no.
equation.
So this is not. So what you're thinking is that, so this is not 0. If they're, even if they're orthogonal, this would not be 0. This is a tensor product.
Okay.
You
Okay,
see
yeah.
that? So
Yeah.
this would be 0 if they're orthogonal, right? That's the difference, right? So
Oh,
what we're
okay.
showing here is this is the orthogonality condition. That's a tensor product.
Okay,
That
got
won't
it.
go to 0. Are you with me? Right? Okay. Okay, so then you can verify that for yourself, that if the states are orthogonal, then you should be able to clone the state, and that's how we can copy classical states. So if we can prepare a pure state, then we have seen that we can prepare an ensemble state, a mixed state, by mixing up different pure states in different weights, right? So then I can get a mixed state like however I want. So far what I have discussed in the last lecture and in this lecture is two things. One is, or three things. One is everything is statistical outcomes. Quantum theory is predicting only statistical outcomes, not individual measurements. We can only talk about probabilities. State fixes the probability distributions. It is not a property of an individual system, right? And we looked at the Stern-Gerlach experiment as a way to prepare the system. We talked about two different things, state preparation and state measurement. And so in the first lecture and up till now, what we have focused is state preparation. And no cloning theorem is also being discussed as a part of state preparation, because if I can prepare one state, then if I am able to copy it, then I can prepare as many states as I want, right? And because that cloning is not possible, right, then because of that no cloning theorem, right, that means that I cannot prepare one state and just simply copy it. So all of this so far, what we talked about is mainly state preparation techniques. I can either relax an atom to the ground state by cooling it down, or I can pass it through a magnetic field and get spin up or spin down, different ways, or I can pass a laser pulse and excite it, different ways to prepare the state. Now we are going to go to the problem of state determination. I think, Mr. Vedveer, you asked about the state determination. Sorry, it took a while, but now we have reached that part, right? So now we are going to discuss how do we actually do the state determination, right? So we have to test or calibrate an apparatus designed to produce a state, right? That is like, for example, Stern-Gerlach experiment. In Stern-Gerlach experiment, when I say I can use Stern-Gerlach experiment as a way to prepare a pure state, that means I'm setting up this Stern-Gerlach experiment, let's say along the x-axis. So the magnetic field gradient is along x-axis. Then I have to actually first put a screen here and pass multiple particles and get these dots where these bands are forming. After that, I can make the holes here. After that, I can make the slits here. So first, I'm measuring the position where the bands are appearing, right? So testing or calibrating an apparatus designed to produce a state itself requires the state determination. So inferring, there's a question. Okay, yes, okay. So the challenge here is that when we are making a measurement, the measurement instrument itself is interacting with the system. So like, for example, when we said for copying, we are making a tensor product, right? Phi1 times psi, right? So this means that these are still separate. That is, whatever my particle is and whatever my device is, these are still separate, that I can treat them as independent systems. But really, when I am making measurements, I am somehow interacting with the system. Without interacting with the system, I am not able to measure the state, right? For example, even if I see, like, even if I shine a single photon or very less intense light on something to see it, that light would have some electromagnetic field which would perturb the state that it is in, right? So let us say I have some psi, some state preparation, I want to measure it. That measurement automatically means that I'm going to disturb the state, right? So if I make the next measurement after one measurement, the next measurement would no longer yield the same result because now my state has changed. So if I prepare the particle in state psi, right, and then I make some measurement on this, right, prepare particle in state psi and make measurement 1, then now my particle state is psi times measure 1. So if I make the second measurement, then I'm going to get a different result, right? So that's why we require, what we need is state determination from multiple measurements. So that's why we make identically prepared systems. So what I would have to do is, for example, in Stern-Gerlach, I have to repeat this experiment on multiple particles that are identically prepared. That is, I heat the oven, I get this silver atom to come out. I need to get those multiple silver atoms to come out to identify which is spin up and which is spin down. I cannot keep measuring on the same particle because every time I make a measurement, the state preparation procedure has changed, right? So more mathematically, right, you can think about if you have some observable which you can express as a Hermitian operator R, right, and you make a measurement, that operator is acting on the state Rn, you get the value, some outcome, right? This single measurement yields only one outcome. There's some question. By this way, measurement depends upon the state preparation as my understanding. No, the measurement itself doesn't depend upon the state preparation. State preparation requires measurement, meaning that when I say that I'm preparing a particle in spin up, what I would have done is I actually set up this Stern-Gerlach experiment and I added the screen. I measured where particles are landing and then I made a slit there. Then whatever particle is going to come out, then that is coming up through this top slit. That means it is spin up, right? Yes, as Mahesh said, the state preparation is validated through measurement. Otherwise, we don't know that we were preparing it in that state. Once we have validated that, then yes, next time onwards, it's whatever it is, right? So it is going to come out, and whatever you measure next, it is independent of the state preparation. But to set up your state preparation, I need to know where it is going. It is like you are taking a survey first and then making the holes at appropriate places. Okay. So returning to, okay, does it mean that during the state preparation we are taking answer? Yes. So for state preparation so state preparation, okay, it is like this. I ask you to make tasty paneer tikka masala. Okay. So then if I ask you to make tasty paneer tikka masala and I give you the recipe, then you're going to cut paneer, you're going to make puree, whatever, and then you're going to mix it up, cook it. Now, how do you know you made tasty paneer masala? Right? You have to taste it. Right? You only after you tasted it, then you know that it is actually that thing was tasty, right? Because the preparation had to be for tasty paneer tikka masala, right? And so I'm doing keto so thoroughly that even my examples have to do with paneer tikka. So anyway, that's a side note. Coming back to that, so you tasted it, so that means that yes, you are taking the ensemble of measurements, and that's how you are able to identify spin up is going to land here, spin down is going to land here, and then you can cut the slits there. Or then you can, after you have tasted it and you made sure that the dish is good, then you can serve it and saying, yeah, this is tasty paneer tikka masala. Does that make sense?
Sir, I got confused with one particle being measured again to get an statistical value rather than taking many particles to get an ensemble value. That's why, sir.
So the one particle that we are, so again, let me clarify, right? So first we are setting up, let's say, Stern-Gerlach experiment along the x direction. I make measurements with multiple copies, right? Identically prepared n particles. So this identical preparation is, I have an oven that, let's say, I'm raising to 600 degrees C, and I have some slit, and these are going through that thing, right? And I have a screen here, right? And then I have all these particles that landed. So this is multiple particles that we have measured. So now I have identified, when I place the screen at some distance d, these particles spin up is going to land here, spin down is going to land here, right? After I have done that, what I'm going to do is I'm going to cut holes here, wherever is spin up, right? Now, if I send next one single silver atom, and if it comes out, I keep sending silver atoms through this, whatever silver atoms are coming out through the slit, they all must be spin up. Do you see that? Right? Yeah. So all we are saying is that we made measurements before to make sure that this is the part where spin up particles land. And when I cut a slit, whatever is coming out of that is, again, like, I can be sure that spin up. It doesn't mean that every time I send out a particle, it will come out through that. So next time, once I have cut a slit and I send a new silver atom, it may not come out through that. It may go land here at spin down. You see? But at some point, some particle will come out of that slit, and whatever comes out of that slit, I would say, is filtered to be spin up along z direction. That is the preparation technique that we are talking about. So in that sense, measurement is involved in the preparation technique itself. But now, if I want to measure what this is, right? If I want to make measurements on this, like, for example, now I want to measure the spin of this, or momentum of this, or something else, energy of this, right? Then I make measurements on this particle. Those are independent of the preparation technique, right? Those measurements are independent of the preparation technique. But you obviously need measurement to set the state preparation itself, because you need to make the slits at a particular, experimentally speaking, you need to make slits at a particular distance. You need to set it up in a particular way, right? I hope that clarifies things there. Are there any other questions? So then, whenever we make a single measurement, again, we are going to not get a statistical ensemble. We are going to only get single outcome. So what we have to do is repeat, prepare and measure, prepare and measure. That is, if I want to see this thing, right? So I have, let's say, Stern-Gerlach apparatus, and I have cut one hole here, right? And I have silver atoms coming through this, and some silver atoms keep coming through this, right? I can make measurements on these silver atoms, whatever I want to measure, right? For example, suppose I want to measure the energy of that, right? So I have some detector that I'm using to measure stuff, right? And as I'm measuring, for that, I have to wait for multiple particles that come out of this top slit. And so I have to repeat this prepare measure sequence multiple times to get the statistical distribution, right? So that's what this thing is trying to say. I'm not going to talk about this phase information right now because we are going to introduce density matrices. And once we introduce the density matrices, we will have a better understanding of the phase information. So I'm going to let that go for right now for relative phases. But what we are measuring when we repeat, prepare and measure, we are measuring these probability amplitudes, and you have to obviously make multiple measurements. So far, whatever we have talked about, although I tried to give a lot of practical examples of how we do this, we are talking about quantum computing and quantum information. So ultimately, we need some physical system that I am able to manipulate. So whenever I talk about computing, I need some system that I can initialize, and I should be able to do some operations, get some results, and then reinitialize, right? I need that kind of standard procedure. If I'm not able to initialize, then basically there is no computation, right? So the IBM quantum computer right now, what it uses is called a transmon qubit, right? This transmon qubit basically is a Josephson junction. A Josephson junction is basically you have two superconducting layers. Let's say you have a superconducting layer, which I'm writing as SC. And then you have another superconducting layer, let's say. And in between these superconducting layers, I'm putting an insulating layer. So this is an insulating layer. And this is another superconducting layer. So two superconductors with an insulating layer, that is what we are calling as a Josephson junction, right? We will talk more about this, right? And I will show you the Hamiltonian and all the math that comes with it. We're just getting introduced. So essentially, what happens is in this junction, there are the way superconductivity is set to work in these are again BCS type superconductors. So these are basically having Cooper pairs. So below the superconducting temperatures, you have Cooper pairs, right? So these Cooper pairs, you can count the number of Cooper pairs. How many Cooper pairs are there? So that the number of Cooper pairs in each one you can say is Ni, right? So you can describe the state like similar to a simple harmonic oscillator. If you recall what we did in the first two lectures, we talked about these operators like A dagger A, right? Creation and annihilation operators, which we can sort of said that you can measure the number of particles, right? So that's how we are kind of talking about number of Cooper pairs in the superconducting films. So I can have in the junction one Cooper pair coming out and being in the junction, or no Cooper pairs in the junction. If there is one Cooper pair in the junction, that is one state. If I have no Cooper pairs in the junction, that is another state. So these are the two states that I am preparing. So if I am at one particular temperature, at millikelvin temperature, then I can achieve a state where there are no Cooper pairs in between in the junction, right? And you attach a capacitor because you want to make it non-linear. We will talk about that, how we make that non-linear. That is to separate the energy levels well enough so that we can access them with microwaves. And then we use microwaves, microwave pulses to do either single shot measurements or multiple measurements to generate new Cooper pairs in the junction. So ground state is no Cooper pairs, for example. And if I have one Cooper pair, then that's another state, right? And by controlling it with microwave pulses, you can sort of operate them. So when we say the junction, what is in the junction, the Cooper pair state, I can express that as psi is equal to some alpha 0 plus beta 1. This does not mean that there is both a Cooper pair and not it is both there and not there in the junction. What it means is that if I prepare identical systems like this, then sometimes I find a Cooper pair there, sometimes I don't find a Cooper pair there, right? The number of times I find a Cooper pair there would be related to beta. The number of times I find do not find the Cooper pair would be related to alpha, right? And so by using a particular microwave pulse at a particular gigahertz frequency, I can set these states. I can initialize these states. So those are the transmon qubits that the IBM quantum computers are using. And by working with this pulse shaping, amplitude, phase, and duration of the pulses, we can precisely prepare the state. And then we can do single runs or multiple runs. So when we make measurements, there are single shot measurements that are fast. That is, I send one single 10 to 100 nanoseconds microwave pulse, and that microwave pulse changes somehow because of its interaction with the qubit, right? So if there is a Cooper pair, that is, it is state 1. If there is a Cooper pair, then the microwave pulse shifts, or it is reflected or transmitted, whatever. Then from the change in the microwave pulse, I can say, okay, in this single shot measurement, there was a Cooper pair. Then I can repeat those measurements, right? The single shot measurement again is not going to give you a statistical distribution. I hope you are able to follow me, right? So here the state preparation is through Josephson junction and dilution refrigerator, and measurement is through microwave pulses. Although we are saying measurement is through microwave pulses, we also use microwave pulses to prepare the state, just like in the Stern-Gerlach experiment where we use the screen to identify where the spin up and spin down is to begin with, right? Similarly, here you can use the microwave pulses and the dilution refrigerator to initialize the state, right? And then following the initialization of the state, I can use microwave pulses at a particular frequency, which matches the difference between having a Cooper pair and not having a Cooper pair. That is the difference between the energy of 0 and 1. And we can use that resonant frequency to make measurements. And these measurements could be single shot measurements or multiple measurements on identically prepared systems, right? So single shot measurement means I send just one pulse. This is often called a quantum non-demolition measurement, QND, right? I send a fast pulse, and then we get some reflection or transmission. There is a question here. What does this dilute refrigerator doing? The dilution refrigerator is basically shielding and setting it to millikelvin temperature. So your superconductor is not going to superconduct at any temperature. So you want to make sure that you are below the superconducting temperature, and you want to have a robust superconductor. Of course, there are high temperature superconductors, but the problem is, in addition to high temperature, it is not like, let's say you take some YBCO kind of a superconductor which can superconduct at, let's say, 135 Kelvin, right? But still at 135 Kelvin, you still have enough thermal energy, and the surrounding electromagnetic field itself may not be in the ground state. So then your qubit, although you prepare in one state, right, your state preparation is not just the Josephson junction. It is Josephson junction plus the background noise. So you want to reduce the background noise and shield the Josephson junction. So the dilution refrigerator is going down to millikelvin to cool it down, to shield it, and to make sure that it is it can be initialized in that state, right, and stays in that state. That was related to one of the other questions we answered previously, that we can maintain this only for, even with a dilution refrigerator, only for milliseconds. But in 1 millisecond, if each fast measurement is 10 nanoseconds, right, or even like, let's say 1 nanosecond, right, you can make 10,000 measurements in by the time it relaxes, right? So you can have multiple single shot measurements. But again, recall that when we keep making single shot measurements repeatedly, what we have to do is we have to prepare and repeat. We cannot keep repeating on the same thing. Then you would get different results, right? And that was there in the notebook that we had yesterday, that if you repeat the same measurement, then you get different states, right? So the single shot measurement cannot capture the full basis state, But the single shot measurement can give you something like how fast things are decaying. So let's say if I have a Cooper pair, how fast it decays, right? That can be obtained through single shot measurement, but it cannot give you like these alpha and beta values. If I want these alpha and beta values, I have to make multiple measurements because these are probabilities. These have to come with multiple measurements. So you have to do a train of pulses, or you have to repeat, prepare and repeat measurement. So to get the quantum state tomography, which reconstruct the full quantum state, that is the density matrix. We're going to talk about density matrix. I was hoping that we would finish this entire lecture in the last hour and do density matrix in this hour, but unfortunately that did not happen. We will look at density matrix soon. So if we can reconstruct the density matrix, basically that gives us the probability distribution, and we know the full quantum state. We know how our preparation procedure is. So if you want to do that, you have to measure in multiple bases. And so for example, if I say, let us say, if I go back to the simple example of my Stern-Gerlach, let me ask you this question. So if I go back to this Stern-Gerlach experiment here, I have made this slit, and let's say something comes out, right? I know that this is along spin up X. Does that give me the entire state? What do you think? Did you understand the question? I use Stern-Gerlach apparatus positioned along the x-axis. The gradient is along the x-axis. I pass silver atoms, and some silver atoms come through the slit that I made where spin-up particles were landing, and they come out. Now, I definitely know that whatever particles are coming out of that slit are spin-up along X. So does this mean that I know the state? So I see two answers. No. Depends upon what we are measuring, right? Okay, that's correct. Depends upon what we are measuring. It is correct in a way, but I would like a more rigorous answer. You are along the right, going along the right line, Shafna. What is a state? Think about what is a state. It is the preparation procedure which should give you what? Probability distribution. Probability distribution for what? For any observable. It should give you probability distribution for any observable, right? So this state preparation technique is only initializing. I only know that the initial state is spin up along X, but I do not know other things. I do not know, whether it is spin up along Y or spin down along Y, or spin up along Z or spin down along Z, right? This is still a superposition in the sense of, right, spin up along Z plus spin down along Z. I don't have, information about that, right? Even this, I could say, is a probability distribution, but even if I forget spin and I think about other observables, right, I do not have that information, right? So we only have limited information. So if you want to reconstruct the full quantum state, then we have to measure in multiple bases. If I just want to reconstruct the full spin, then I have to measure in multiple bases, and these are called rotation gate pulses. We will see what these rotation gates are. So essentially, the transmon qubit that I am describing, this Josephson junction, when we write the Hamiltonian, you will see that there is a rotation element. So you can use the microwave pulses to rotate from, you can use the, like for example, yesterday we have seen something called, when we are doing the Qiskit, we have seen something called the Hadamard gate. So what Hadamard gate does is, if I take state 0, right, and apply Hadamard gate, it gives me a superposition of this, right? This is like a rotation, right? Meaning I was spin up along X. Now I go to Z, right? I rotate from X to Z, sort of like that. So you can use microwave pulses to apply microwave pulses in the right frequency and in the right way to use as rotating gates. And then we can measure in multiple bases and repeat these measurements on thousands of trials per basis to estimate the expectation values, like sigma X, sigma Y, sigma Z. So the sigma X, sigma y, and sigma z are called the Pauli matrices, right? Sigma z is, you can think of that as 1, 0, 0, minus 1. Sigma x would be 0, 1, 1, 0, right? And then this is, I think, is this 0 minus I 0? Is that right? Right. So now if I combine this with identity matrix, right, which is 1, 0, 0, 1. These form the basis for expressing any two-dimensional matrix. I can express any two-dimensional matrix in terms of these four matrices. So, okay, there is, okay. So I can express any matrix in terms of these four matrices, right? So I could write any matrix M as some I plus some, let's say, Cx with sigma x plus Cy, sigma y plus Cz, sigma z. Any matrix M, I can in general express it like this, where Cx, Cy, Cz, or maybe I can write C0 also. As a combination, as a linear combination of these four matrices. Density matrix, for this, if I am measuring like, a two-state system, the density matrix would be a 2 by 2 matrix. So even the density matrix, I should be able to express like this, right? So you can also put like, sometimes people use a factor of half. So if you put up, if you see factor of half, that is just like when you do like this. Here I'm just writing it as 1 minus 1, but it is actually half minus half. So you can ignore that factor, right? But the idea is that this Cx is basically expectation value along this. This is expectation value along what? This is expectation value along Z. So by measuring along multiple bases and doing repeat measurements. So to measure this is a, when I put the expectation value, that means this includes thousands of measurements, right? And I have to do those thousands of measurement along different bases. Then I can do complete quantum state tomography and establish my density matrix. And this density matrix will capture coherences, that is off-diagonal elements. These off-diagonal elements capture coherences. We will see what that is. And they reduce errors from noise, give you high fidelity systems. So you can do things like error correction, gate verification, and so on and so forth. But the point that I want to make in this lecture is transmon is coming through this Cooper pairs in a Josephson junction coupled with a capacitor, which is like a non-linear anharmonic oscillator. And we are using that along with microwave pulses to prepare the state and measure the state. To fully measure the state, we need to measure in multiple bases. Single shot measurements with the microwave pulse gives me only one outcome. It cannot give me the density matrix. If I want the density matrix, then basically I have to repeat measurements, not just repeat measurements, but repeat them along different bases to get my full density matrix, which would give me the off-diagonal elements, which have to do with coherences, which we will talk about more in the next lecture, right? So one measurement again, here again, I'm talking about Grover search, and we will talk about these in more detail. I do not want to go into these right now, but it looks something like this. We put these gates and use frameworks like Qiskit to apply these gates. So what we are going to do later on is we still need to catch up more on density matrices. And once we are caught up on density matrices, then I want to introduce more about transmons and multiple qubits and talk about entanglement in more detail. And once we have talked about entanglement in more detail, then we will discuss how actually we realize these systems, right? That how we would do quantum algorithms or different actual quantum information and quantum computing on these things. So that's where I would like to stop about the state preparation and state determination. And then I quickly want to make two comments about the uncertainty relationship, which I have made again previously. So now we have seen that whatever measurement we make, that measurement is coming from not from single outcome, multiple outcomes, right? So if I have, let us say, if I have a tungsten filament, which I am heating, right? So let us say I'm heating it to 1600 C, whatever, which leads to thermionic emission, right? And so I get these electrons out from this tungsten tip. So I know that these electrons are coming from the tungsten tip, but I do not know exactly which tungsten atom it is coming from, right? So one electron may come from here, another electron may come from here, another can come from here, right? It may come from different tungsten atoms. So they're identically prepared in that they're coming from the same tungsten tip, but still there is some variation in the sense that they are coming from different tungsten atoms within the same tungsten tip. So as they are coming out, I can measure the energy, right? Or I can measure the position, right? So I can say this electron is coming out, right? And at some point I can put a screen here, and let us say this electron, I see a localized hit here. So then I know where it is with respect to the tip. So I can measure its position R, right? After it hits the screen. Similarly, I can also measure momentum. Like for example, I could put a photo gate, or I could put some other way to measure energy. I can put another magnetic field. So I know it is coming it with this velocity. So if I apply a known magnetic field along particular direction, I know the charge of electron and I know the magnetic field. And if it deflects from the deflection, I can back calculate what should be this V, right? So I can measure the momentum or I can measure the position. So for each individual electron, I can get a hit. So when we talk about uncertainty, let us say I talk about uncertainty in position delta X. This delta X is an uncertainty in position of multiple measurements. So I'm getting multiple electrons, one after another. And then I am making a histogram, right? I'm making a histogram, right? So that is, I say, okay, this is my different spread of X values. So some number of particles land at X is equal to 0. Some other particles land at X is equal to 2. Some land here, some land there, right? So this spread, some sort of a Gaussian spread, I'm saying that is the delta X. Similarly, I could make momentum measurements. But note that when we make measurements, I cannot measure, suppose I measured the position, right? I cannot measure momentum on it again, because by measuring position, I have changed the state. It is no more the same state preparation. Now, the state preparation would be electron coming from the tungsten tip plus interaction with the detector. So then I cannot measure the momentum. I can either measure position or momentum. Even the position also, I cannot measure position once and position again, because once I have measured it, I have changed the state, right? So we are preparing identical particles and measuring them multiple times, right? Sorry, measuring them identically prepared in multiple copies. And we are making a statistical distribution. And that is where we are getting uncertainty from, this delta X. It is coming from a statistical distribution. There is no delta X for a single measurement. So when a particle falls here, there is no meaning of saying that for this one particle, there is uncertainty in position of delta X. That is meaningless. The delta X is in the statistical distribution. It is this delta X and delta P, right? I can also measure momentum like with this QV cross B, for example, and make a distribution. Then I get delta P, right? So it is this delta X and this delta P. That is in the uncertainty relationship, that is greater than or equal to H bar by 2, right? It is not on a single measurement. It is on a statistical uncertainty, right? On multiple measurements which are on identically prepared system. I hope that makes sense, right? Again, I would like to mention that a lot of people do not understand this. They think that delta X and delta P are single measurements. They are not. There is no meaning to uncertainty delta X for a single measurement. It's just meaningless, right? So please don't be confused thinking that delta X and delta P belong to single measurement, right? So that said, the final thing that I would like to cover today is to do with entanglement, which we will talk about in more detail again in the next lecture when we discuss density matrices. So by entanglement, what we mean, again, whatever we are talking about, superposition, entanglement, like Priyanshu mentioned earlier in the chat, it is statistical or ensemble, right? So whenever you see a quiz question, it has to do with statistical or ensemble. So entanglement means that when I make multiple measurements, let us say I have two particles, and I make multiple measurements on these two particles. That is, I have some sort of a preparation technique, right? I'm preparing some two particles, right? And one particle, let's say, goes this way, another particle goes this way. I make measurements on these particles, right? Not on single particles. I make measurements on multiple particles prepared exactly the same way. And then I see that whatever I measured here on the left side, whatever measurements I get on the left side, the statistical distribution is correlated to the statistical distribution on the right side. The operating term is correlation. So if there are correlations in those measurements, that is what we call as sort of entanglement, right? But really, there could be correlations, but no entanglement still. But we will say that these correlations are what appear as entanglements. So entanglement is again a statistical feature that comes from correlations. It is not a single particle feature, right? And so when we talk about a state, the state is fixing the probability distribution, probability outcomes. And so when we say two particles are entangled, what we mean is that we the measurements on those are correlated. So this immediately resolves a lot of things, like, for example, in the Copenhagen interpretation and even in the EPR paradox, right? The unnatural explanations that Einstein talked about are not required anymore. In the sense that if I take one electron here and another one on the moon, right, and then I measure it here, then how does it know to flip down, right? So how does information travel so fast? Is there non-locality and things like that? These become much easier to discuss when we talk about entanglement as a correlation, as a statistical feature, which is very, again, important for quantum information and quantum computing. So in the next lecture, we will talk more about density matrices and entanglement. And I would like to show, using Qiskit, how we can make measurements, these single shot and multi-shot measurements that we discussed. And then we will also talk about the basics of transmon qubits. So with that, I would like to stop here. And I would like to relaunch the poll that we had earlier. So please answer these three questions. And after you have answered these three questions, if you have any further questions, you are welcome to stay back and interact. If you do not have any questions, that will be the end of lecture for today. Roy has a question about quantum walk. In these also, are we discussing states and not a single particle? Yes, whenever we talk about a state, it is a probability distribution. So it is not a single particle. So anything that has, when we talk about any quantum state, no matter what it is fixing the probability distribution. I hope that answers your question. Okay, I think I'm going to end the poll now. So if I hope everybody answered. Okay, still I see that a couple of people answered that de Broglie relation is best understood as a statement about instantaneous momentum of the particle. So please, again, like we saw this in the beginning. So maybe either you are having difficulty understanding, or you are not paying attention. So please, see why that is incorrect. And if you're paying attention, you should have picked up on what Priyanshu said, and you should have picked the statistical as the answer, right? This one, very good. This, everybody got it right. And this, everybody got it right. Okay, that's great. Thank you, guys. So that's all for today. And with that, if you have any questions, I'm going to hang around. But if you don't have any further questions, you are welcome to leave. Thank you.